Hello, my name is Marta Payá, researcher in the Institute of Automática Informática Industrial in the Universitat Politècnica de València. During the last 2 years, I was studying of the master's degree on automatics and industrial informatics. Moreover, I did my master dissertation in the European project MSCA Rise Endorse of Marie Curie Rise Action, and I will introduce you my work on it. This is the table of contents that we are going to expose. We will start with a brief introduction to the project. Then we will put it in context, and we will also talk about the working environment. We will continue with a brief analysis of the problem and talking about the tools required. We will also talk about the design and development of the proposed solution, to finally conclude with the test and results, implementation of future works, and a brief conclusion. The proposed objectives for the ENDORSE project are to conduct research and development towards a cost-effective logistics robotic system for healthcare and commercial spaces, to push forward the frontier of human-robot interaction for logistics application where robots navigate in crowded spaces, to research and develop robust localization methods for infrastructure-led indoor fleet localization, and to introduce novel cloud services that bring together solutions from healthcare, robotics, and logistics. And the personal goals during this project are a study of the tools to be used, EAs of ROS environment, and a study and development of an algorithm from centrally controlled flow. ENDORSE project is a consortium of international and national universities and companies. An example of this area is the Institute of Automática Informática Industrial of the Universitat Politècnica de València, where me and my project mate, Sandra Moreno Olivares, are working to advance on ENDORSE project. The main goal of this project is to bring robots to hospitals and residences to carry out logistical or even sanitary tasks. The robots will be tested in full-scale mock-up replicas of healthcare centers within the consortium members' premises at the end of the ENDORSE project. For this project, it's being carried out technical and coordination meetings for sharing information between the different parts of the project. About the Instituto de Automática e Informática Industrial is located in the Parque Tecnológico of the UPV. Since November of 2019, I am working as a researcher in the IDOS in the ENDORSE project. This institute mainly covers 5 fields of the research: robotics, industrial computing, process control, graphics and multimedia computing, and computer vision. My work on the ENDORSE project are focused on the area of robotics. Our task in the ENDORSE project are human-aware path planning. This task consists of robots being able to move around the environment without problems. In the image of the left, we can see the robot that we are going to work with. The robot on the left is in A2. This robot is an RB1 with a robotic arm and a bionic hand to manipulate objects. To its right, we have an RB1-2, in this case with a lifting platform which allows it to transport heavy loads. And finally, we have a mobile diagnostic center. In the image of the right, you can see a photo of the entire team of ENDORSE partners. The first contact with robots was a study of the interaction with the environment, as we can see in the video. Tests were carried out with inflation. We did tests with the robots crossing paths with people, like in the video on the left, or with other robots, like in the video on the right. In February of this year, the audit was carried out, in which we obtained a very positive report. Robots were located on the map and avoidance each other. But in future tests, we observed that this work was delicate and slowly, and it was very difficult to escalate. This problem led us to think and develop a solution that would limit the number of robots in different rooms. This solution will minimize the possibility of blockages between robots. In this solution, I wrote my master dissertation, with the name Centralized Control of the Influx of Mobile Robots in a Plant with More Than One Room. First, we carried out an analysis of the problem, where we structured the project and divided it into 3 main parts: master nodes, robots, and communication channels. The master node will be executed on a cloud service. The communication channel that we will use is MQTT, running different MQTT bridges on each robot. Finally, for robot programming, we are more limited, because when we acquired the RB1 from the robotic company, it has installed Linux 16.4 and ROS Kinetic. Even so, we can choose the programming language that will be Python. In the word tools, we divide the problem into two categories, hardware and software. Regarding hardware, the main element is the RB1, which the main characteristics have been studied to no possible limitations. We have divided these characteristics in mechanics, informatics, and sensory, as you can see in the table. Regarding software tools, we start with robot operating system. ROS is a framework that provides a working environment for robot programming. It enables low-level device control like sensors, communication between them, so inter-process communication, and facilitating programming through packages management. These packages are made up of launch files, source code, compilation rules file, and dependencies file. In the image, we can see a ROS environment where 4 nodes have been launched, which communicate with each other through topics. Regarding master node, which name is Fleet Management System or FMS, it has been developed by Centro de Investigación en Gestión e Ingeniería de la Producción of UPV. This device plays an essential role. The service will be launched in a service cloud, and its main functionalities are path generation and task management. This FMS must know the situation of each robot because if an user requests a task, the FMS must calculate which robot fulfills this task with minimum cost. Regarding MQTT Bright, it has been developed by the Valencian company Robotnik. MQTT is a communication protocol developed at 1999, which has been very famous because of its low use of resources and its TCP-oriented connection. In the case of our MQTT Bright, its name is Command Interface, and it's based on ROS package MQTT Bright. This package allows translation between ROS topics and MQTT topics and vice versa. Finally, since a lot of work has had to be done with simulation environments due to COVID-19, what has for us to reinvent ourselves, we must to comment RBIS and Gazebo programs. RBIS is a ROS-oriented simulation tool which allows you to visualize in real time where the robot is and what it's detecting through all its sensors. This tool is very practical both in simulation and in real environment. Regarding Gazebo, it is a tool fully oriented to simulation, especially in the field of robots, even allowing to design models and maps. For the design of the solution, it has been proposed that FMS, which is already capable of generating roads, allows dividing a map into different areas so that they are restricted to a limited number of robots in the case of being rooms very critical, or that we know that cause blockages, such a corridor. When the robot is going to enter an unrestricted area, the FMS will check if it can do it. In the case it cannot, it will send the robot a waiting signal. When the room is deleted, it will allow the robot to continue with its objective. This is possible thanks to the constant feedback between the FMS and the robot. For the MQTT Bright, the main modifications have been in the configuration file, where new correspondences between ROS topics and MQTT topics have been added. So if we send a message to the topic endorse robot cross stop, it will translate into ROS environment in the topic RB1 base cross command manager stop. If we send a number 1, we will ask to the robot to stop, and if we send a number 0, we will allow it to continue. To prepare the environment, scripts have been provided, which use the command docker run. These scripts launch the simulation environment on our computer. In these images, we can see the maps that have been provided to us both in RBIS and in Gazebo. For launch the MQTT Bright, a script has been provided which launch the command manager node. This node is ready to interpret commands like go to or move. Now, to this command, we would observe the following. As we can see, the robot moves to its target. For the ROS application, 3 Python files have been developed. The stop subclass file that subscribes the stop topic in order to check if the robot has been requested to stop. The command subclass file that subscribes the command topic in order that if a robot is requested to stop, it stores the objective it was fulfilling to remember his initial objective. The app file that manages the data provided by the 2 previous classes, importing them to develop the required functionality. In the test and research part, we made a division between the test in simulation and in the real environment. Regarding the simulation, we have a video which has been accelerated and in which we can see how we have worked. First, we launch the simulation environment. Here we have three robots in the map in this frame. Next, we launch the MQTT Bridge and prove that we can connect to the MQTT Bridge. And we launch the application that we have developed. We throw that target to robot 2 in this case, and we see how it starts the movement, as we can see in the video. And then we request to the robot to stop. We see how to. Next, we send a command asking the robot to continue with the movement. Regarding the real environment, we have made the relevant modification in the code because working in simulation is sometimes different from working in a real environment. We send a position to the robot, as we can see in the video. When he is going to change his room, we stop him by MQTT, as we can see in the video on the right, emulating that the room he is going to access is restricted. And finally, when the room is related, we allow it to continue, as we can see in the video. Regarding implementation, comment the postponement of the timelines due to COVID-19. And for future work, we will be interested to complete the development of the project. In addition to adapting the application for use in buildings with more than one floor, and also adapt the application for cleaning in times of COVID-19. We can conclude that the first two objectives proposed have been met, while the last one has been partially met because the FMS needs to be complete to test the algorithm developed. We will highlight learning in new tools and technologies such as RB1 or Docker, which has allowed us to acquire important skills for future projects. Furthermore, the fact of participating actively in an international project has allowed us to value communication within the project. And we can highlight too the work in the following transversal competencies. These are application and practical thinking, analysis and problem resolution, teamwork and leadership, knowledge of contemporary problems, and planning and time management. Thank you for your attention, and if you have any doubts, don't hesitate to contact us.